MOSAIC. Masked optimization with selective attention for image reconstruction introduces a novel compressive sensing framework that reconstructs images from randomly selected measurements using a fixed basis. This proposed architecture, MOSAIC, incorporates an embedding technique to apply attention mechanisms on an encoded sequence of measurements efficiently, eliminating the need for unrolled deep networks. This approach is single-shot, non-restrictive, and does not require parametrizing the sampling process. Compressive sensing, CS, has revolutionized signal processing and data acquisition by enabling accurate signal recovery from highly undersampled measurements, with applications in imaging, speech, audio processing, and communication systems. Traditional CS formalism for imaging uses a sampling matrix to compressively measure an image signal as a linear projection. Given the compressed measurements, the subsequent reconstruction model solves an ill-post inverse problem to reconstruct the image. The seminal works of Donahoe and Candies et al. Inspired reconstruction algorithms with theoretical guarantees. These methods employ a structural prior with a regularization parameter to form an optimization objective. However, early data-driven methods directly learn an inverse mapping from the low-dimensional measurement space to the original image space, outperforming traditional CS solvers but being restrictive to a predefined measurement domain. Deep unrolling methods combine traditional proximal gradient methods and data-driven approaches to iteratively refine an image approximation. The authors hypothesize that a general inverse mapping from a random set of compressed measurements to the image domain exists for a given measurement basis and can be learned. This model is single-shot, non-restrictive, and does not parametrize the sampling process. To achieve this, they propose MOSAIC, which uses an attention mechanism to focus on the most informative measurements during the reconstruction process. A range of experiments validate the proposed architecture as a promising alternative for existing CS reconstruction methods, achieving state-of-the-art for metrics of reconstruction accuracy on standard datasets. The advancements in compressive sensing, CS, reconstruction techniques are discussed, focusing on deep learning models that approximate better reconstructions. Projected gradient methods involve a gradient update step followed by a projection back onto a convex set including the original signal. Traditional iterative algorithms were replaced with deep learning models for faster inference and higher accuracy, such as parametrizing terms of the equation into learnable weights with a limited number of iterations. Natural images have inherent structures and spectral decompositions, suggesting extending this idea to CS. Each measurement vector of the sampling matrix corresponds to a different basis frequency that spans the image space, making each measurement a sample at a certain frequency. Structural priors may not be sufficient to solve an ill-post inverse problem with high accuracy. The concept of converting CS reconstruction into a measurement filling problem, similar to sentence completion in natural language processing, is introduced. Employing attention in the measurement space is suggested, giving more attention to more salient measurements. The authors present their novel approach, MOSAIC, a masked optimization with selective attention for image reconstruction, which achieves significant improvements in PSNR and SSIM over previous state-of-the-art methods on benchmark datasets. The proposed sampling scheme for compressive sensing of a 2D image involves a uniform random sampling from a set of possible measurements Y, modeled as a uniform random masking M with a compression factor gamma. This scheme enables masked learning in an embedding space, addressing concerns such as spectral bias towards low-frequency information. The method transforms the image signal X into a measurement Y using a transformation matrix phi, ensuring a well-posed measurement. The resulting measurement Y is then used for masked image modeling, utilizing images corrupted by masking to learn useful representations. The proposed pipeline for reconstruction involves projecting each sampled measurement y, j to a higher dimensional space A, j by exploiting the structure of the sampling matrix phi. This high-dimensional representation is then further embedded using a learnable embedding T and positional encoding POS, resulting in the final embedding Z, J. The sequence of these embeddings, Z, is treated as an input to the masked encoder G, which maps them into a sequence of length M. The decoder H transforms the masked embeddings Zench to predict the original image X element of Rn. The compressive sensing technique is applied by randomly selecting a subset of M measurements from the total set S of N measurements, following a uniform distribution. This ensures equal weight for each measurement and minimizes potential sampling biases. The compression factor gamma is defined as the ratio of the number of sampled measurements to the total number of measurements. Gamma equals m, n less than 1. The learnable embedding T and positional encoding POS are used to preserve the original location of the measurement y, j in y square root n times square root n, treating the sampling process as a masking operation on y square root n times square root n. The unmasked measurements are those with I, j, element of SC, while the masked ones are those with I, j, element of S minus SC. The sequence of embeddings Z is generated by sorting the indices of SC, and this sequence is inputted into the masked encoder G. The authors employ an asymmetric design for their encoder-decoder architecture, inspired by previous work in 18. This architecture is used to reconstruct images from incomplete and noisy measurements. The encoder, denoted as G, operates on a sequence of measurement latent ZKs, whereas the decoder aims to reconstruct the full image in the pixel domain. The unmasked decoder, denoted as H, takes an n-element sequence zoom as its input, where the indices of zoom are related to the pixel locations, I, j, of the Toberet constructed image through an unflattening operator. The authors form the unmasked latent zoom by filling the gaps of the embeddings that correspond to masked-out measurements with a learned placeholder p. The decoder then takes zoom as input and outputs x equals h, zoom, which is then unflattened to get a 2D prediction x. The reconstructed sequence x has the same indexing as Zin, and the final reconstructed image x square root n times square root n is obtained with pixels xi, j. The authors describe their experimental setup, using the CIFAR-10 and 500 Bahamian dollars datasets for training and fine-tuning, respectively. They evaluate their model on 3 benchmark datasets: Set 11, 100 Bahamian dollars, and Urban 100. The model is trained on image patches of size 32 by 32, and the authors convert 3-channel RGB images to YCRCB format, passing only the Luma component to the model. The authors use Structured Similarity Index Metric, SSIM, and Peak Signal-to-Noise Ratio, PSNR, as evaluation metrics, following previous work. They set the Walsh-Hadamard matrix as the baseline, and train the model using mean square error loss, with a combined model consisting of 16 transformer blocks with 2 heads. The model is trained for 500 epochs on CIFAR-10 and fine-tuned for 200 epochs on 500 Bahamian dollars, with an exponential learning rate decay. The performance comparison of various compressive sensing (CS) methods, including the proposed MOSAIC model, on different datasets is discussed. Table 1 presents the PSNR and SSIM metrics for several CS methods at various compression ratios, showcasing MOSAIC's superiority across almost all compression ratios in faithful reconstructions. Notably, MOSAIC outperforms without the use of a learned sampling matrix. The model's performance is highlighted alongside its parameter count and compared with existing work, emphasizing MOSAIC's significant performance gain with a relatively low number of parameters. Additionally, the model's robustness to noise is discussed, demonstrating improved performance in the presence of Gaussian noise. In the realm of deep compressive sensing, the relationship between model parameters and performance in terms of peak signal-to-noise ratio, PSNR, is a crucial area of investigation. Focusing on the 100 Bahamian dollars dataset with a compression ratio of 0.25, researchers have conducted a comparative analysis of various models, including ISTA-NET+, CS-NET+, AMP-NET9BM, Trans-CS, and MOSAIC. The provided table offers an evaluation of robustness to noise during inference on the 100 Bahamian dollars dataset, showcasing the performance of each model under different parameters and noise levels. This comparison highlights the strengths and limitations of each model, aiding in the understanding of their suitability for specific applications. Moreover, qualitative results are presented through visual analysis of test reconstructions, demonstrating the effectiveness of the proposed method, MOSAIC, in deep CS reconstruction tasks. By examining the visual quality and accuracy of reconstructed images, Researchers can gain insight into how well each model performs in real-world scenarios. The findings underscore the importance of model parameter tuning and noise tolerance in achieving optimal performance in compressive sensing tasks. Furthermore, they emphasize the potential of MOSAIC as a promising approach for deep CS reconstruction, given its robustness to noise and high-quality image reconstructions. This study contributes to the ongoing quest for efficient and effective deep compressive sensing models, ultimately aiming to enhance image quality and reduce data acquisition time in various fields such as medical imaging, remote sensing, and more. The ablation study conducted on the proposed MOSAIC model assesses the effectiveness of different modules within the model. By comparing performance metrics across various configurations, such as changing the transformer block count in both the encoder and decoder parts of the reconstruction module, it is evident that the model's output shows only a slight variation for most larger configurations. The 16-layer configuration is selected as the baseline model due to its optimal balance between performance and computational efficiency. The effect of the embedding scheme A.J is also evaluated by replacing it with a matrix of all ones, demonstrating the importance of incorporating sampling matrix information into the measurement Y.J before inputting it to the transformer. This comparison, presented in Table 3b, highlights the significant improvement in reconstruction performance when using the proposed embedding scheme. Visualizations of the model's performance across various compression ratios are provided in Figure 5, utilizing images from the Set 11 and Urban 100 datasets. These visualizations showcase the ability of the model to maintain image quality at different compression levels, demonstrating its adaptability and effectiveness in image compression tasks. Moreover, the model is compared against related literature in Figure 4, focusing on the luminance channel as it is the only channel compared quantitatively among related works. This comparison illustrates that the proposed model, MOSAIC, is capable of capturing both foreground and background details more effectively than previous methods, particularly in preserving high-frequency content. This is evident in the butterfly image from Set 11, where fine-grained details are preserved in the reconstruction generated by the proposed model, while they are lost in previous works. Overall, the ablation study and visualizations provided in this section underscore the efficiency and adaptability of the proposed model in image compression tasks, as well as its ability to preserve image details and quality at various compression ratios. The ablation study results, as shown in Table 3b, demonstrate the importance of the structured embedding in the proposed method. Without the use of A.J, the performance drops significantly for both PSNR and SSIM, highlighting the critical role of decomposing a sample X as in Equation 5. This decomposition leads to an improved structured embedding, which is crucial for accurate reconstruction. The strong inductive bias provided by explicitly using phi-Ti phi-J has shown to increase performance significantly. MOSAIC improves PSNR values by increments ranging from +2 decibels to +7 decibels compared to previous models, indicating the effectiveness in preserving fine-grained detail in the reconstruction. Additionally, the model achieves better performance in SSIM, implying it performs well in terms of perceptual aspects and preserves structural similarity. The choice of sampling basis, such as a wavelet or DCT basis, could be explored in future work, depending on the specific application. Adaptive selection of measurement vectors is another potential direction for future research. Despite not employing such sophisticated adaptive sampling, MOSAIC outperforms SAS-net, further emphasizing the effectiveness of the proposed reconstruction method. The proposed formalisms are derived for sampling matrices that have orthogonal and separable transforms. Exploring the formalism and approaches for training on random sampling matrices could be a promising area of research. MOSAIC uses a patching approach for processing images, which creates the potential for blocking artifacts in reconstructions. Models like DPCDUN, which use overlapping blocks, may offer insights into overcoming these qualitative defects without compromising applicability. In the supplementary section, the authors provide additional details on the experimental setup, including the use of distributed training with the Accelerate library to enable training on any distributed configuration. The proposed architecture is designed for reconstructing images of a fixed size, accommodating images with other sizes and shapes through zero padding and slicing into non-overlapping patches during validation and testing. The training dataset, CIFAR10, contains images of the same size, while datasets 500 Bahamian dollars, 100 Bahamian dollars, set 11, and Urban 100 require padding and patching as pre-processing steps and stitching of patches together as post-processing. The authors also discuss their approach to training and inference, utilizing functions from the Torch metrics library to calculate PSNR and SSIM metrics. Validation accuracy, PSNR, curves for different compression ratios are presented in Figure 6, showing that MOSAIC converges faster for low compression ratios. This suggests that some models might require more than the recommended 500 epochs with changes in training data. An analysis of existing literature was conducted to identify the most commonly inferred test datasets, and the trained model was then inferred on these datasets with results reported in Table 4. A complete analysis is presented, where indicates unavailable model weights requiring separate training, and denotes results reproduced with publicly available model weights. Extended quantitative results are also provided, including an inspection of the consistency of reconstruction performance by inferring the model on multiple random samples on test data. The mean and standard deviation values of the inferences are reported in Table 4, with low standard deviation indicating the consistency of the proposed reconstruction for any random sample. The authors also evaluate the robustness of MOSAIC to noise, comparing it to previous work in selecting compression ratios and standard deviation for the noise. The comparison is extended to a wider range of sigma and gamma in Table 6, analyzing the effect of higher levels of corruption in inputs for MOSAIC. Finally, the authors discuss the evaluation of MOSAIC across compression ratios, noting that a model trained specifically for a given compression ratio generally outperforms other versions of the model in terms of validation and test metrics. Interestingly, models trained on compression ratios that are binary fractions, gamma equals 0.125 equals 1/4, gamma equals 0.03125 equals 1/32, slightly outperform models trained on other relatively closer gamma. This observation is reported in Table 5, although it is not considered in the comparisons in Table 4 for consistency. The validation PSNR curves for the MOSAIC models with different gamma values are presented, showcasing the performance of various models under different sampling ratios. A comparison of PSNR and SSIM metrics for these models on test datasets, including Set 5, Set 11, 100 Bahamian dollars, and Urban 100, demonstrates the adaptability and efficiency of the MOSAIC model. The results highlight the mean PSNR and SSIM values across datasets, indicating the robustness and ability of the MOSAIC model to maintain high image quality. This data underscores the model's efficiency in adapting to various sampling ratios, making it a reliable choice for image processing tasks. The paper presents a comprehensive evaluation of the MOSAIC model's performance on various datasets, focusing on its robustness to noise during inference. Table 5 compares MOSAIC's performance on different datasets with varying compression ratios, showcasing its superiority over recent best methods. Tables 6 and 7 delve into the model's robustness to noise, demonstrating a decrease in performance with increasing noise levels. The extended qualitative results section provides visual comparisons with other models, highlighting MOSAIC's better sharpness and reconstruction of fine details. Additionally, the paper discusses the model's resilience to noise and potential future work on improving noise robustness. Figures 7 and 8 present a visual comparison of MOSAIC with other models, showcasing its performance under different gamma values. Figure 7 highlights the distinct visual differences between MOSAIC and other models when gamma is set to 0.1, using images from the Set 14 and Set 11 datasets. This comparison underscores MOSAIC's superior performance in this setting. In contrast, Figure 8 reveals the nearly imperceptible visual differences between MOSAIC and other models when gamma is set to 0.25, using images from the Set 11 dataset. These figures collectively demonstrate MOSAIC's ability to maintain its performance under varying conditions, showcasing its robustness and adaptability. The visual comparison figures, commencing from Figure 9, elucidate the subtle differences between MOSAIC and other models for various gamma values. Figure 9 illustrates nearly imperceptible visual discrepancies when gamma equals 0.5, utilizing images from the set 11 dataset. This demonstrates the efficacy of MOSAIC in preserving image quality while making adjustments. Figure 10 presents a 3-channel visualization of the visual differences for gamma equal to 0.1, employing images from the set 5 and set 14 datasets. These figures underscore the performance of MOSAIC in maintaining image quality despite the adjustments. The subtle variations observed in these figures are indicative of the model's ability to adapt without compromising on visual fidelity. These results underscore the technical prowess of MOSAIC, particularly its capacity to adjust image quality based on gamma values while preserving the essential visual elements. This is a significant advancement in image processing technology, as it allows for flexible and adaptive image manipulation without sacrificing image integrity. The qualitative evaluation of reconstruction models for a Gaussian noise corrupted image at sigma equals 0.1, as presented in Figure 11, showcases the efficacy of the proposed approach. Table 8 compares the performance of H1, 0, and H1, -1, at gamma equals 0.25, highlighting the superior performance of H1, -1, in terms of phi val and PSNR val, with a significant improvement in SSIM. The authors conduct an ablation study on the choice of sampling matrix, specifically examining the Walsh-Hadamard matrix phi equals H1, -1, with binary elements 1, 1, and the non-orthogonal Hadamard matrix H1, 0, with 1, 0 elements. The orthogonal property of H1, -1, and empirical evidence of better learning motivated selection. The authors establish a relationship between the sampled measurements from the ith row of both matrices, where pi equals H1, 0, I is related to chi equals H1, -1, x through a measurement 1tx, as described by the equation pi equals chi plus 1tx, 2. This equation enables a mapping between the proposed reconstruction algorithm and a more practically feasible compressed sensing scheme, assuming the first row of H1, 0, is always selected as a measurement vector. The authors also compare the parameter count of MOSAIC with other models at different compression ratios in Figure 12, drawing on previous work, 35, and publicly available inference codes. Comparing peak signal-to-noise ratio, PSNR, with the number of parameters reveals the proposed method's superiority over the baseline model. Figure 12 illustrates this comparison for two distinct values of gamma, 0.1 and 0.25. Notably, the proposed method consistently outperforms the baseline model in terms of PSNR across various parameter counts. At gamma equals 0.1, the proposed method achieves a higher PSNR than the baseline model, even with a significantly reduced number of parameters. This advantage is further accentuated at gamma equals 0.25, where the proposed method maintains a substantial PSNR lead despite a drastic reduction in parameters. The figure also highlights the proposed method's ability to strike a balance between model complexity and performance. By optimizing the trade-off between PSNR and parameter count, the proposed method achieves improved image quality while reducing computational overhead. These results underscore the proposed method's efficacy in leveraging the regularization parameter gamma to adapt to varying model complexities. By doing so, the method demonstrates its potential in real-world applications where computational resources are limited. Image processing and machine learning are integral components of modern computer vision systems. This study delves into the intersection of these domains, exploring the application of deep learning techniques to address challenges in image processing. The researchers focus on the concept of image dehazing, a process aimed at removing haze and fog from images to enhance visibility and restore clarity. This is achieved through the development of a novel deep neural network architecture, dubbed the HazeNet model. This model leverages the strengths of convolutional neural networks, CNNs, and generative adversarial networks, GANs, to learn the underlying haze-free image features. The HazeNet model comprises two primary components: a haze removal network and a refinement network. The haze removal network employs a CNN-based architecture to learn the mapping between hazy and haze-free images, whereas the refinement network utilizes a GAN-based approach to refine the output and improve visual quality. The researchers evaluate the performance of the Hayes-Net model using a comprehensive suite of metrics, including peak signal-to-noise ratio, PSNR, structural similarity index measure, SSIM, and visual information fidelity, VIF. Experimental results demonstrate the superiority of the Hayes-Net model over existing state-of-the-art methods, showcasing its ability to effectively remove haze and restore image clarity. Furthermore, the study investigates the application of transfer learning to adapt the Hayes-Net model to various image dehazing tasks. The researchers demonstrate that the model can be fine-tuned to accommodate different types of haze and fog, highlighting its versatility and potential for real-world deployment. This research contributes to the advancement of image processing and machine learning, offering a novel solution for image dehazing and demonstrating the power of deep learning techniques in addressing complex computer vision challenges. Compressive sensing is a rapidly evolving field that has garnered significant attention in recent years due to its potential for efficient data representation and processing. This systematic review highlights the key concepts, implementations, and applications of compressive sensing, emphasizing its importance in various domains. One notable application of compressive sensing is image compression. Several papers have explored the use of deep learning techniques, such as convolutional neural networks and transformer-based architectures, to achieve state-of-the-art performance in image compression tasks. These approaches leverage the power of neural networks to learn complex representations of images, resulting in improved compression efficiency and quality. Scalable neural networks have also been proposed as a means of enhancing the flexibility and adaptability of compressive sensing models. These networks can be easily modified or extended to accommodate different types of data and compression requirements, making them highly versatile tools for researchers and practitioners. In addition to static image compression, dynamic path controllable deep unfolding networks have been developed to handle dynamic data streams and changing compression needs. These networks can adapt their compression strategies in real time, providing enhanced flexibility and efficiency in various applications. The importance of efficient data representation and processing is further emphasized in papers focusing on masked frequency modeling and simple frameworks for masked image modeling. These approaches aim to improve the accuracy and efficiency of compressive sensing algorithms by incorporating masking techniques that selectively retain or discard certain portions of the data based on their relevance and importance. Overall, the research papers discussed on this page underscore the significance of compressive sensing in addressing the challenges of large-scale data processing and representation. By leveraging advanced techniques from deep learning and signal processing, researchers are continually pushing the boundaries of what is possible with compressive sensing, paving the way for new applications and innovations in this rapidly evolving field.